चालेल ये नेक्स्ट डिले होणार
हे तुम्हाला खरं फास्ट कनेक्शन द्यायला पाहिजे ना नेटवर्क तुम्ही सांगितलं ना कम्प्युटर सेंटरला इथे या व्हिडिओ स्ट्रीमिंगला तुम्हाला फास्ट ते कनेक्शन द्यायला पाहिजे
थोडं आज हे दिसतंय नेटवर्कचा थोडा प्रॉब्लेम दिसतोय सर नाही तर नेहमी असतं
Come, keep your bag there.
So I think some issues there with the webmail.
Oh, is that right?
Yes, because webmail was not working.
Oh.
Server was down.
Oh my. Yeah, because here also the network is a little flaky. In fact, probably no, it's showing a network right now. No? Yes, it's showing. Yeah, it's showing the network. Network, internet access, दाखवतो.
ते हॉटस्पॉटवर येते ना
Oh, अच्छा अच्छा.
त्यामुळे स्ट्रीमिंग
Oh, I see. नेटवर्कचा काही प्रॉब्लेम आहे का
सर नेटच गेलाय सर
ओ अच्छा मी कम्प्युटर सेंटर ऑफ नेटवर्किंग in the course on foundations of wavelets. I'm sorry that we had to delay the commencement of the session due to some network problems at our end at IIT Bombay. The chat window. Okay, so
sir, suggest some books or for discrete wavelet transport, wavelet simlet.
Oh my goodness.
Because I couldn't find any clear picture about these two wavelets.
Tour of signal processing. I think it's available in Indian edition now. These are fairly advanced. I'll just say a little bit about them. See, in fact, coiflets, the term coiflets was, coined after one of the researchers in wavelets, Koifman, right? And simlets and coiflets, is that right?
Yes.
So in fact, he will say a little more about them. And if you look at the book by Stephen Malat on a wavelet tour of signal processing, I'm sure you will find many of these notions discussed in some detail. Madhumita. So please let us know if we've answered your question. Yeah. Yes, Kishore, please.
So, like for practical applications, one can look into the existing documentations of software. Like two very good resources are MATLAB and Python PyWavelets website, and the MATLAB Wavelet Analyzer Toolbox. There we can find from the application perspective also, and from a little bit on the theoretical insights also about these individual wavelets like coiflets, simlets, and other like Dubash wavelets also. Like there are some like quite a wide range of discrete wavelets are given in these software packages. So it's a good resource to look into it.
Thank you. So Madhumita, have we answered your question? Please let us know. Yeah, I'm also sorry that we had to delay the start of the session because of some network issues at this end.
Yes, sir. Thank you, please.
Okay, very good. So now let us have more questions and more interaction from the other Madhumita or the other participants. Maybe the participants can begin to introduce themselves so that we know who is participating in this session, and you can tell us what you're doing, where you are from, and anything else that you would like to share.
One more question.
Yes, she has one more question. Yes, Madhumita. Oh, you've retracted no, you need to type the question again.
Okay.
How to find the filter banks for these two wavelengths. Now both of these filter banks are biorthogonal, am I right, Kishore? They are both, if I'm not, I think I'm reasonably...
Sorry, they are orthogonal.
Orthogonal? Okay. Coiflets and similets, yeah. So how to find, see, you will have to, if you're asking how to design an orthogonal filter bank, then that is discussed in detail in the course. How to find the filter banks, see, it begins, so typically, I'll give you an example. For example, if you take the Dobushi filter banks, the starting point is you want to impose the maximal number of vanishing moments. Now, in these coiflets and similets, you are not interested in imposing the maximum number of vanishing moments, right? So then you have a lot of flexibility on what the filters can be, let it satisfy some other criteria and so on and so forth. Yes? Well, the only way is to see the tab. If you're interested in looking at how they were arrived at, then I would recommend the book by Malat, A Wavelet Tour of Signal Processing. But if you are interested in looking at the tabulated coefficients, then those should be available. So if you're just looking at the implementation of coiflets and similets, then you will find the tabulated coefficients. So it depends on what you want to do. Would you be able to comment on what would be a good source? I think she's asking what would be a good source probably for the...
So for the structure of the filter bank, so that is the same structure. For example, if you look at the simplest case of the 1D wavelet transform, so it is suppose the implementation is a discrete wavelet transform filter bank, and the structure is same for both there's coiflets and the other one similets, and the coefficients can be found there is a website called PyBytes. So it's a website, they have listed a lot of, means all these families, like all the wavelet families coefficients up to from length 2 to I think around 36 around.
Oh.
So one can, so I will post in the discussion forum,
Yeah,
the
you
link
can
of
post.
the
So Kishore will post so Kishore will post some resources in the discussion forum to enable you to get more insights into these two kinds of wavelets, the coiflets and simulets. Fine. Is that what you wanted, Madhumita? Anything else? So with the other participants, okay, how they differ from Haar and Dobushi. See, the Dobushi filter banks use the maximal number of vanishing moments. So the moment you impose maximal number of vanishing moments, the filter bank becomes unique, and that is the Dobushi family. The moment you depart from that, that is, you relax the number of vanishing moments required, then you can get so many other classes of families. Coiflets and simulets are examples of them. Right?
Yes, so from the implementation perspective of like decomposition and reconstruction, like analysis and synthesis part, structurally they are same. There is no difference. But what suggested is how, on the more deeper aspect, how like the design part of it. But the implementation part of it, if we have the filter bank coefficients, for example, that the website that I said PyBytes, they give there is listed, actually they are publicly available in many other domains. I am just giving one example. So from that structural perspective of how the filter bank is designed, from the like maybe 5 levels of decomposition and then reconstruction, all will be same. Only the coefficients will differ. That is available on that website that I will post. The website link I will post in the forum.
And by the way, Haar is the first member of the Dobushi family. That should be understood. So the Haar is the shortest possible Dobushi wavelet. With the maximum, it has only one vanishing moment and that's it. Right? Can't be anything more. So Haar and Dobushi, that way, they are all of the same family. I don't offhand remember the coefficients for coiflet and simlet, but could you elaborate, could you write the full form of CSV that you have in mind? Anyway, how do you find the wavelet transform of time series? In general, the time series is the input to the filter bank. So you subject it to the action of the two-band filter bank. That's how you will find.
There is one more question.
Yes. Yes, Babu. Is wavelet signal processing linear or non-linear?
Yes, sir, you are audible.
Okay, so I think I'm audible, right? But not visible. So it doesn't matter. I hear Babul asking, is wavelet signal processing a linear or a non-linear signal? It's a linear. Where the wavelet transform by itself is linear. right? So it obeys the principle of superposition. However, wavelet transforms are often followed by nonlinear operations. So for example, you could conceive of a kind of union of wavelets and machine learning in the scattering transform. In the scattering transform, one follows the wavelet transform by the modulus nonlinearity. So and then it's often true that one follows the wavelet transform with a nonlinearity to achieve something more. So is that your question, Babu? And Pankaj's question is being answered. So I answered Pankaj's question. His question pertained to essentially the wavelet transform of time series. So we are trying to understand his question better. And my PhD student Kishore my teaching associate Kishore is trying to answer it. So Babu, have you answered your question? So can the other people in the chat introduce themselves? You can ask more questions, Madhumita, Pankaj Kumar, Babu. So can the other participants introduce themselves in the chat?
Okay, so
Could you tell wavelet transform library in Python or MATLAB? Okay. Okay, we are answering your question on chat. Pankaj, does that answer your question? Kishore has answered your question on the chat. Even in Scilab is the open source version of MATLAB. There also I think some wavelet tools are available, I'm told. No? Scilab, is it available? I don't know. I think they were trying to put some tools in open source also in Scilab. Okay, so Pankaj's question. So Pankaj, anything further that you want to ask us or discuss? And Babul, Madhumita, can the others also introduce themselves?
Are wavelets used
Okay.
in
Are wavelets used in AI applications, in image processing, image analysis and other general? Yes, indeed. That's a very good question. See, I'll give you 2 or 3 different contexts. One is that Stephen Mallard, somewhere around the middle of the last decade, came up with the scattering transform. So the scattering transform is a way of not only for images, but it's also for whether it's audio that's one-dimensional or two-dimensional. One could use the scattering transform as a very economical and interpretable kind of union of wavelets and machine learning. In addition, one could of course do a wavelet transform followed by a CNN, or a wavelet transform followed by some other machine learning AI kind of structure. They are indeed very useful in wavelets and AI applications. In fact, our PhD, my PhD student Kishore will tell you a little bit about, what he has already published and so on, So he can tell you a little bit about how he has been trying to bring together waves. So it's a good question. In fact, wavelets, and there is a lot of scope to bring together wavelets and AI. Yeah, now I'll hand over to Kishore.
So like as mentioned in the image processing, so in image processing there is a lot of use cases of wavelets. For example, like the JPEG is a very standard example, which is a application of wavelet transform. Similarly, for other images like biometrics, it is very useful. For segmentation, it is very useful. Like my personal PhD project is, one of my application is the brain MR image segmentation. So where I am using wavelets to identify the features from the image slices. For example, both in the 2-dimensional and 3-dimensional, it is helpful. Like for example, a brain MR is inherently a 3D volume. So I use a 3D discrete wavelet transform to extract the low frequency, high frequency edges, these type of features from those images. So they are essential. One most like helpful, like where I find key, it is helpful key, it leads to the compressed CNN networks, like the without wavelet based networks, then it compresses almost to a scale of 10 times and more. So in that sense it is quite useful, like wherever there is a case of representing data in some organized manner, there will be a use case of these type of representations, wavelet type representations, for example.
Very good. It's a nice explanation. In fact, now I'll take up Ajit Rajlakshmi's question. So she is a mathematics teacher trying to learn wavelets. In the first two assignments I couldn't score well. Okay. Yeah, no problem. I think if I understand correctly, we are probably going to take only some of the best scores or something like that, right? In this course. Anyway, whatever it is, don't worry. If you have not done well in the first two, I'm sure you will be able to do well in the next assignment. So please continue to put in your best. Don't be discouraged by, a little bit of oscillation in performance in the initial phase. I hope you are understanding the lectures, Raj Lakshmi. So, are you understanding the lectures in the course? And, while you answer that question, let me take Madhumita's question. How to learn about lifting scheme in wavelets? Because it is difficult for me and it's no clear example. See, in fact, in this foundation course, we have taken only based on the first few lectures of my NPTEL. I have a course in NPTEL. I have, a full set of almost 40 lectures in NPTEL, where in the later lectures I have talked a little bit about the lifting scheme. I will briefly explain it to you here. The lifting scheme essentially is a way of doing what is equivalent to a ladder structure. So, you decompose the lattice, one stage of a lattice into one upper triangular and one lower triangular matrix. So basically, you update in the lifting scheme, you update one of the two branches of the two-band filter bank in one go, and then in the next step you update the other branch, right? So it's an alternation between updating the low pass branch and updating the high pass branch, and thus achieving what one stage of a lattice structure would achieve. So in a way it involves decomposition of the lattice matrix. Now I have explained this in detail in the later part of the lectures. The lattice structure for wavelets and so on. And how to realize the lattice structure for the Dovershi family and so on, right? So I hope that answers your question, Madhumita. It is there in my later, but not in this foundation course of 1 month. It is there in my set of, and you will be able to find it. You go to NPTEL, you go to the NPTEL site, and there you can look for my wavelets course, which is a 40 lectures, Advanced DSP, Multirate Systems and Wavelets. So have you seen that course, Madhumita?
Found on YouTube.
Okay, very good. Found it in YouTube. So Madhumita, you find the one on the lifting scheme in YouTube or the general lectures? lifting scheme. So further questions or anything that you want to interact? Okay, there's a question from Babul, I think. Okay, there's a question from Babul. I'll just take that up. Are DWT and CWT linear transformations like the Fourier transform in wavelet signal processing, linear or non? So wavelet transforms are in general linear, right? They are linear. Say so also, whether it's a discrete wavelet transform or continuous wavelet transforms. However, the DWT or CWT is often subjected to nonlinear afterwards for applications, right? So inherently it's a linear transform, but it can be used in nonlinear signal processing because that gives you more useful interpretations or outputs afterwards. For example, wavelet denoising requires the wavelet transformation followed by nonlinear operations like thresholding, hard thresholding, soft thresholding, and so on. So, do we have any other questions? Any other interactions that you want to have? Or should we close the session now if there are none? Alright, so I don't see any further questions or any further interaction. So then we will bring this session to a close. Thank you so much. A very good evening to all of you, and I do hope that you are enjoying the course. And please feel free to post questions on the discussion forum, which Kishore is keeping track of. Yes, and then we hope also, you may also want to tell us whether you would like to have a more elaborate course on wavelets. This is a 1-month course, but whether you want to have, and how many of you might be interested if we offer a course which brings together signal processing and machine learning, or wavelets and machine learning. You may want to express that to us. Yes? Okay. So is multirate signal processing linear or non-linear signal processing compared to wavelet? See, multirate signal processing again in general is linear. So multirate systems are linear. But again, non-linearities are included along with multirate systems often. Multirate signal processing is also a vehicle for realizing wavelet transforms. Multirate systems by themselves are linear, but they are not shift invariant. They are shift variant systems, multirate systems. Does that answer your question, Babul? Very good, Babu. So it's good to know that you would like to learn about wavelets and ML. So we've been contemplating creating such a course and we'll plan it out slowly. All right, then if there are no further, anything more from any of the participants, if not, then we will once again express our gratitude for participating in this session and we'll bring this session to a close. Thank you and a very good evening to all of you.